We've seen a number of cases or examples where we took the forward Laplace transform. However, sometimes you need to work your way backwards. If we're not interested in the function of s but a function of t, then we better be able to work our way from s's back to t's. The phrase we use for this is inverting the Laplace transform, just like an inverse function undoes the effect of a previous function. For example, find a function whose Laplace transform is 2 over s squared, or notation-wise, L to the negative 1 is the inverse Laplace transform. And notice this only makes sense. There's some really good guidelines here. We have to have s's in this thing that we're inverting because we're going from s's to t's. So the inverse function takes s's to t's, and the regular Laplace transform has a function of t in it, and it gives us back s's. So just keep that in mind as you go through the process. In this particular instance, we're asked to work backwards from 2 over s squared and ask, well, what function of t would have given rise to that? Well, what we do here is we scan down the table, and we see that we have an s squared on the bottom, and that's all there is. So the closest match would be this function here. Looking at this carefully, if we want 1 over s squared, that would be the same as that table entry with n equals 1, so n plus 1 is 1 plus 1 over 1. So this is a bit more of backwards thinking. How can I match this template to the function I was given? Well, I can look at this and say I need an s squared. The way I get an s squared is by having n equals 1. With that in mind, we can actually go through a staged process of this. We know that the transform of t to the 1 would be equal to 1 factorial, which is 1 over s to the 1 plus 1, which is 1 over s squared. Well, what do we have? We have 2 over s squared. Well, how would we achieve that? Well, the only thing missing is that 2 multiplier. So if we had the transform of 2 times t, we would end up with 2 over s squared, and that would be what we're looking for. Then all we do is change the order here and say I'm interested in the inverse of the 2 over s squared, and that equals the 2t by itself. So if I took the Laplace transform of 2t, I would end up with 2 over s squared. So the inverse transform of 2 over s squared is 2t. With a bit of practice, this becomes more clear. Looking at this example here, we're asked to invert 5 over s minus 2. We scan down the list, This is definitely a match to this form here with a equals, we have s minus, a is going to equal 2. So what we could say immediately is the inverse of 1 over s minus 2 is going to be e to the 2t, e to the at. We can further refine that then and say the inverse transform of 5 over s minus 2 is going to be 5 e to the 2t. These are steps that we wouldn't necessarily show every time. If you can see the inverse transform through its table entry, we would just copy down the answer that we know is correct. But this shows how we can build up towards the transform of a more complex function. We've implicitly assumed here, we're going to make it explicit here, the inverse Laplace is also linear. If the inverse is linear, then we can take advantage of that and say, well, we have the inverse Laplace of 1/2 times 1 over s plus the inverse of s over s squared plus 4. Then we can look at each of these members individually, and we can look at the 1 over s. Hey, that's exactly in our table already. And then we can look at the s over s squared plus 4. Notice there's 2 close relatives here. If there's an s on top, it's the one that goes with cos. If there was just a constant, then we would have the transform of sine. So we have a perfect match to this with k equals, gotta be careful here, this is 2 squared, and so this is a transform with k equals 2. Then we can immediately jump from the entries on this side to their original functions of time. Here we have a half The 1 over s is the direct transform of 1, so we'd simply have a half times 1. Again, using that linearity, a coefficient can be brought out front if it helps. And here we have simply cos of 2t. Again, we're back to a function of time only, having started with a function of s, and we simply looked up each of these functions in the table of the transform versions and tried to work our way back to the originals.